All right. So, kia ora koutou, ko Alvaro tōku ingoa. I'm Alvaro Orsi. I'm the data science lead at PHF Science. And today I thought that I'm going to introduce this concept of digital twins that are powered by AI and why we believe that that we can essentially leverage AI as a force multipliers for this type of systems. Very quickly, so you know what to expect, I'm going to cover 4 main topics. Digital twins in general, ALMA, which is the digital twin that we have developed at PHF Science, and you heard about it yesterday. I want to have a few words about sovereign AI and concept of a national digital twin and what that entails, and why it would be cool that more people participate in this. So let me start by, since this is the AI Researchers Conference, I thought I would start by just discussing a little bit of research and why I am interested in digital twins in the first place. And there was this paper from literally 20 years ago that prompted me to follow a career in computational cosmology. So back in those days, the coolest thing that I could possibly think of was to simulate the universe itself, right? So that front cover is the result of an n-body simulation with trillions of particles, that due to gravity, they try to simulate the entire universe, and I thought that was the coolest thing. And that's really the concept of a simulation, so not exactly a replica of the universe, because you're not trying to match exactly how the universe looks like, but you're trying to construct something that is statistically, essentially equivalent to the real universe, right? So that's essentially a model. It's got limited data, because although you do collect a lot of data, we're talking about the universe, right? So limited data, and you rely mostly on incorporating knowledge about first principles, right? In this case, the laws of nature themselves, right? Including gravity, right? The cool thing of working in simulations, as you know, is that simulations can be manipulated, right? You can move them and twist them and, try what would happen if I do this and that. And that's really cool because you learn a lot, by changing things. Evolves in time. You can use it to predict the past. You can use it to, you try to reproduce the present, and you could even forecast the future if you wanted. So I think from a research point of view, digital twins are the equivalent of working in simulations, but something that, in the context of something that could actually have, for example, some business or economic, or community social value, essentially. That's how I see, essentially, the transition. Digital twin is just another term for the concept of simulations. And there are other types of simulations. So this is another project where, a few years ago, we built digital twins of kiwi fruit orchards. And in this case, the idea was essentially to help growers to understand their kiwi fruit orchards in a much better way by creating a digital replica of them, right? In this case, this is data-rich in the sense that it was built using LiDAR, using satellite imaging, using hyperspectral imaging, and lots of proximal sensors, to measure ground truth. And it also had a layer of physical modeling. In this case, we wanted to model the photosynthesis process and how the 3-dimensional geometry of an orchard can have an impact on these things, right? Normally, when we talk about digital twins, and probably historically speaking, digital twins, we refer to digital replicas of a thing, right? And by thing, an asset, right? Like a space telescope or an airplane, or an engine, those type of things, right? Although I don't like to define things specifically because I find that too limiting, you can talk about different attributes of digital twins, right? You want your digital twin to be powered by multiple data streams. You also want to ideally be able to manipulate your digital twin. So in the case of a space telescope, you want to see what happens if the mirror is bigger, what will happen if there is a power cut, etc. Right? And it also evolves in time, attempting to replicate the real-time state of the real thing as well, right? So that's kind of my brief introduction to the concept of digital twins. The reality is that digital twins as a concept has been used across many different industries and sectors, right? From retail to manufacturing, smart cities, aerospace, supply chain, and so on. The challenge here is that these digital twins that are sector specific, they don't really talk to each other very well. These are different communities of engineers and researchers that put together these projects. They all have different features, they all have different standards, different data standards, because they have different uses, right? And so it's really difficult to actually define what a digital twin should be. Well, this is a conversation that about 7 years ago was actually a very hotly debated topic, and it led eventually in the UK to the development of the Gemini principles. Mm-hmm. The Gemini principles are seen as a sort of a design principle for the construction of digital twins, right? And these principles should help you understand essentially how to get the most of your digital twin idea. I like to think of these as essentially having three main pillars. Digital twins should have clear purpose, digital twins should be trustworthy, and they should function effectively. To me, that means a digital twin is not just a pretty animation like the things that I showed before, but it's actually something that can deliver value. It does something useful, right? And that's the concept. So, years ago, digital twins was something that people talked about a lot, and actually today, this is the hype cycle of emerging technologies that you probably all are very familiar with. Just, a very opinionated way of describing, the expectations of different technologies. It's interesting that digital twins essentially disappeared from this diagram, except that concept there of a digital twin of a customer, which is really something different. And it's been completely replaced by, generative AI and that sort of thing, Obviously, generative AI is probably very close to the peak of inflated expectations. Some say that it's actually coming down into the disillusionment trough. I don't know. The interesting thing is that back in 2018, when people were discussing and debating these Gemini principles, digital twins were at the peak of the inflated expectations, because that's what everyone in industry was talking about. Just like then they were talking about big data, blockchain, and blah, blah, blah. Interestingly, no one talks about digital twins anymore. I've just been trying to exaggerate a bit. Of course, people still talk about digital twins, right? My point here is that, even by 2018, people realized that digital twins were really going to become useful and deliver value in a scale of 5 to 10 years, right? My sort of proposition here is that AI is the driving force of the Gemini principles, which allow digital twins to become useful things today. Maybe not 7 years ago, but certainly today. And I'm going to explain briefly what I mean by this. So you remember that the Gemini principles consisted on three things, which is purpose, trust, and function. In terms of purpose, AI offers a whole breadth of different capabilities that are actually technologies that at this stage are mature enough that you can think of them as tools. They're not research projects. They're not at the cutting edge of university research, but they're actually things that are fully productionized, And I would refer, for example, to the Weka AI platform, that Albert showed us yesterday as an example of AI and machine learning, readily available for this type of things. So predictive machine learning is an extremely or a very mature piece of technology now that you can leverage for this type of systems. Optimization, of course, automation, computer vision is probably, arguably the most mature AI technology available to us nowadays. And NLPs and LLMs, what-if analysis, and machine learning for data streams. These are all parts of, of a toolbox. They're not just research disciplines anymore. The other one is trust, and I think this is a really interesting one. I would refer back to the presentation we had yesterday about this sort of, how we discuss bias in AI systems and how that sort of risk is overstated. I think what you can definitely say is that there is plenty of research about fairness, aware machine learning systems, bias mitigation, etc., which again is readily available. It's not just an academic exercise, and it's something that you can leverage in your own systems, right? Responsible AI frameworks are also everywhere. So you can't just say, oh, we need to think about the risk and blah, 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 because there are frameworks already available for anyone. So building trust, and perhaps the other thing is explainable AI, feature importance, causal discovery, symbolic regression, you name it. I mean, there is plenty, that we can leverage. And finally, in terms of function, how do you ensure that these systems actually do what they're supposed to be doing effectively, right? And they're not just pretty visualizations. So you have plenty of research and capabilities on AI on edge. You have systems, that you can deploy GPUs even on edge. Even you can explore the use of large language models on edge as well these days. Federated machine learning is an incredibly useful and interesting concept that maybe ties with the whole idea of data mesh, so distributed systems, right? I would say one thing that is now perhaps coming out of the research or sort of the cutting edge area is this idea of multi-agent AI networks, which I find fascinating in the context of bridging the gap between systems that may not speak the same language, but they can have an agent playing as an intermediate to translate, for example, different data standards, right? So MCP servers, being sort of the next iteration of just a simple API, right? That is a rigid thing, right? Data, concept drift, correction, adaptive learning systems, etc. So that was my point. Now I wanted to describe how did we get onto this area, and this is probably a journey that started a couple of years ago. And just for context, I wanted to show this dashboard, which is still live, as far as I know. It's a wastewater dashboard. The URL, I think, is actually still poops.nz or so, because it's wastewater data, which was incredibly relevant at the time of the COVID pandemic to trace, essentially the amount of COVID in the communities as traced by what was found in wastewater treatment plants, right? I can tell you, by working closely to the researchers, to the team that is behind, the collection and the aggregation and the analysis of this data, that it's incredibly difficult to come up with, the number of genome copies per liter, for example, in a wastewater sample. So to translate from a wastewater sample to saying there is this much COVID in this community, I think that's an incredible feat. However, ultimately, what you end up with in the end is just a nice plot that shows you, how much COVID is in the wastewater and whether it's going up or down, right? So we were struggling with understanding how can we exploit, this data further. It's already difficult to collect it and to make sense of it, but we've done it. The next step is how can we make the most out of this data, right? So obviously, the answer was going to come through machine learning models and time series modeling and so on, so that we can, for example, predict quantities that may be useful, etc. The challenge here was actually trying to link this back to individuals, right? The wastewater testing is not telling you how many people are getting COVID. It's only telling you how many genome copies the thing is able to find, you know? So there was that connection with individuals and with what individuals do and how they behave and how that relates to something, you know, that is essentially dependent on social dynamics, you know, like infectious disease and outbreaks, etc. So that led us to start thinking about how to build an AI system that actually takes into account individual dynamics. And that is ALMA. So then we reformulated the problem into the challenge of understanding complexity in modern decision making, right? So if you're able to understand social dynamics and population dynamics, right, then you would know that from a policy perspective, any policy that is being drafted will have an impact on areas that go well beyond that specific policy, right? An example is public health, where, you know, during the COVID times, there will be a lockdown because of it's a public health response, but that lockdown is going to have an impact on, you know, unemployment. It might have an impact on crime. It might have, you know, multiple impacts, and it's really hard, in principle, to anticipate all these effects, right? The reason why it's hard is because traditional methods that support that decision making are very descriptive, right? They're not really predictive, right? And so these methods fall short, you know, out of, you know, if you just rely on descriptive statistics, there isn't much intelligence that you can bring to the table. And the other one, a more practical problem, is the data scarcity problem, right? The fact that we just don't have enough data, we don't have enough data of enough quality, or our data is too disparate. You know, you have different surveys here and surveys there, and how do you combine them? How do you build a full picture, right? So this is why we thought that the way to go forward was to build essentially a digital twin of the population itself, right? And this is our goal. So for me, in order to explain what this digital twin of a population means, I thought I was going to play with these animations now to show you very briefly what this means, right? A digital twin of the population doesn't mean that we're trying to map every single real individual. You know, so these two guys here, they're just representing, they're essentially virtual representations of our population, but they're not real, right? They are virtual Kiwis. They're actually built from aggregate data. They're not built from individual level data, right? But the key is that the attributes of these individuals will resemble those of real people, right? Let me explain now how do we actually do this. So the key here is around building a synthetic population, you know? And in terms of data, the most important data source for us comes from stats and set, essentially the census data, also complemented by the integrated data infrastructure, which we also heard yesterday. So, like I said, we want to go to the individual level of data. We want to simulate individuals without really going into individual records, right? We don't want personal information. And we actually don't care. I don't care what every individual does, but I do care about how they contribute to the statistics at any reasonable scale. And in that case, the scale of interest here is SA2s for us. So now let me show you this. This is representing an SA2, you know, it's just completely bare in this case. So the first thing that we do is that we place our individuals, our virtual individuals, in this SA2. We know how many people live in every SA2. So on average, I think it's about 1,000 people, maybe 1,500 people per SA2. So you can think of them as suburbs. And we place these individuals. We know that there are 1,500, so we can extract actually the distribution of age, the distribution of sex, the distribution of ethnicity, you know? There are challenges already there. It would be really easy to do it in a sort of randomly sampling, you know, from these distributions, but we want to make sure that we that we maintain essentially the internal correlations between these things, right? So that would be the first step. The second step, and very important, is to give them a place to live, right? So leveraging, again, data from Stats and Set and from other sources like LINS and even OpenStreetMap and so on, we can actually localize, geolocate every household within an SA2. So we can start essentially now populating those households with individuals, right? So household occupation, we know, and the geo-assignment of households, essentially meaning this virtual individual, this is where you will live, and this is your household, your family, if you like. You're going to live with all these people in this house. This is also done in a way that we preserve, the internal correlations, Like, for example, most of the time, people with, for example, the same ethnicity will live together, just because this is how most families are. But these are things that are actually all derived from the statistics that we have available. So we're not making those decisions. We're not making assumptions. We're using what's in the census and the IDI, And so in order to do this and to make sure that we control those internal correlations, we use iterative proportional fitting, which is a technique that essentially allows us to take into account all the different attributes of the individuals. Then the next step is to start giving them occupations to our agents. So kids will go to schools given their SA2. We know how many people goes to school. We know the composition of schools, but also universities, and also people going to work. When people go to work, we have commuting surveys that tell us how many people from this SA2 will move to adjacent SA2s, and that's why the woman there is jumping, to that other SA2 to go to work, right? Because we know how many people do this, and we know this in terms of their demographic attributes as well. So we can start assigning all these activities to our agents. So this includes also people that are fully employed, people that are part-time working, people that work from home as well. We know their industries, and we know the distribution of incomes as well, and so on. So those are all the things that we start assigning to our virtual individuals. The other one is, there's a little car there, because we want people to actually start moving around our cities, because we know that they go to work, well, they can make use of the road networks that are available, again, from OpenStreetMap and other services, so that they don't move in straight lines, but they actually utilize the road network, so we can compute commuting patterns and so on. They also have other activities, like they have time to chill out outdoors, they go to stadiums, they might go to the pub, to church, etc., to hospital. And all this data comes from different surveys, from census, from IDI, and the beauty of working in this synthetic population concept is that it allows us to aggregate both data that comes from census, which you would deem as very complete and very thorough, but also data that comes from smaller surveys, right? Because it's a synthetic population, we can aggregate data at different levels. That it gives us that power. So we know that the people, will spend this many hours, in an outdoor activity and so on. They will go to school, they will go to the pub, etc. And we start making those assignments, based on this time use survey, workforce survey. So because we know how many hours people spend at work, we can actually construct life diaries for every individual as well. And finally, the other bit of this is that there is also the interaction of our synthetic population with the environment, and this is what turns our synthetic population into a simulation of agents, actually, because these agents are people that they don't just exist, but they actually do things, and they respond to changes from the environment, right? So you might remember from one of the presentations yesterday, we were discussing that we can use this platform to study the impact of heat waves or air pollution on the population, right? Because we can compute the cumulative exposure of our agents to these environmental conditions, right? And then we can simulate how they react to these changes, you know? Similarly, we can also compute, you know, for example, the progression of a disease, because our agents, you know, go to the supermarket or go to different places. They might interact with each other, right? So this is the main concept behind a synthetic population. So it's not just a table of synthetic individuals with attributes, but it's actually a dynamic. It's actually a dynamic simulation where these people actually do things, and we can again manipulate them. We can study the impact of interventions, etc. You know. So before I move on, I just wanted to acknowledge that this is the work of many people over a couple of years. You know, so this is my team, and we work, as you see, you know, data scientists, AI engineers, and data engineers, and so on. We also work with students. So just a small promotion, you know, in this case, right now we're working with students from both Auckland and Canterbury University, but we're open to, you know, engage with students from any university. So we will be very happy to actually, because we always need more hands to work on different aspects of this synthetic population. So if you want to reach out later and discuss potential student projects, I will be very interested in. Okay. So now let me show you how this platform actually looks like, you know, not in an illustrative way now, but now for real. We called it ALMA, as in Aotearoa large scale multi-agent platform. And it's an actual platform. It's something that you interact with as a user, right? It allows you to visualize the interplay of different factors. It also allows you to discover hidden interactions from different you know, machine learning, predictive machine learning you know, components that are in this. It also allows you to simulate the future, simulate what-if types of scenarios, and so on. So, like I said, that's how it looks like. And just as you can see, there are multiple components. I will just quickly go through some of these, like the synthetic population, life diaries, and the routing is something that I showed you before. I'm just going to show you now how it actually looks like within the platform. Like I mentioned, we have all these attributes for our 5 million synthetic Kiwis that occupy, you know, populate the entire country, and those are some of the data sources that we use. And this is how this actually looks like. So this is you know, this is an example of the actual user interface, which, as you can see, is a geospatial user interface. I'm going to play this. Here the user is just exploring a specific suburb in Auckland. Every one of those smiley faces represents a synthetic individual, right? And now you see that you can press play, and now you see the people moving around, right? This particular simulation is centered on a primary school, and the histogram that you see on the left shows you the number of people that are coming into that location as a function of time. Because it's a primary school, most of the occupation is between the 9 and 3 p.m., right? And as you saw, as we got closer to 9 a.m., you saw that influx of kids coming into the school. And now the user is just clicking on every synthetic individual, and that gives you a visualization of their life diaries. So you see that people actually have activities, and they do things with their time, right? So that's the level of granularity that we can achieve with this concept. I mentioned before that we also embedded a microtraffic simulation into ALMA. So because we have the locations, we know that people go, you know, they will be going from A to B at 3 p.m. So instead of just drawing a straight line between the two, we actually make them go through the road network. And this is really powerful for us because it allows us to explore. It's not just cool for the visuals, but it's also cool because it allows us to explore, for example, the impact of disruptions. What would happen if something causes a road closure. For example, what would happen if there is a flooding event? What would happen if there is an earthquake or a tsunami, whatever, or simply a road closure, right? That would mean that our agents would need to recalculate their routing, in order to get to, to different points. So this is what we do. The next one on causal inference and multivariate time series modeling is essentially what prompted the whole concept of ALMA in the first place, right? These AI predictive components are already embedded within the platform, so the user can activate them if, make use of some time series data that is already included in the platform, or they can bring their own. At the moment, for example, we are exploring this capability to simulate the statistics of crime victimization across New Zealand. So there are very rich time series data in terms of crime statistics and so on. And the cool thing here is that we are leveraging two machine learning-based capabilities. One, multivariate time series models, which allows us to essentially predict or forecast the future, particularly forecast when you create disruptions in your time series, like what would happen if crime is actually 20% lower than what you think. How would that have an impact on another parameter? You can study these things. And causal discovery and causal inference allows you to disentangle this curse of machine learning models, that they don't distinguish between causality and correlation, right? Causal inference does, or causal discovery. At least it's built so that you at least can attempt to disentangle these two. So this is an example. I also thought since here this is an audience of researchers, I would just spend a minute describing that we've implemented a transformer-based time series model to address or to make use, like I said in the beginning, we wanted to exploit the power of this wastewater testing. So we are bringing, as past covariates, a system that, very much receives multiple time series as input. So things like COVID admissions, COVID in wastewater, and COVID variants, and so on. But it also admits future covariates, things like holidays, and the month of the year, etc. Things that that will happen in the future, right? And the architecture allows us to bring these two things together to make predictions, right? And this is roughly how those predictions look like. The gray line is the number of hospital admissions for COVID, and the colored ones are our model predictions. As you can see in the beginning, this it works really poorly. So we don't have enough data, but you see that as the model gets retrained with more and more data, it starts improving its predictive capabilities. So it's a really cool concept. And that capability is, as you know, agnostic of the use case. I mean, the architecture itself could be used for any type of multi-source time series problem. Just a word about the geospatial user interface, which actually relates back to the synthetic population itself. We've taken a lot of care, especially over the last year, to avoid hard coding the development of our synthetic population to be specific to New Zealand, specific to the structure and the format of the census and IDI data, because we want our synthetic population to be our method, at least, to be as general as possible. And so one way of doing this is that we've created a digital twin also for Tonga. This is leveraging some of our collaborations and some of the domain expertise from our Pacific group, who actually work in Tonga and other Pacific nations on supporting the water resource management there. So we've actually gone and created a synthetic population for Tonga. We've also incorporated the ability to ingest remote sensing data. So from satellite imaging, those pixels that you see there are representing PM 2.5. So essentially, it's this is a heat map, essentially, of, you can think of air quality, right? The amount of particulate in the air, right? So we can start exploring now how people in Tonga are exposed to different levels of pollution, of air pollution, right? And this is what we've done. So this is an example on the top of the synthetic population demographics that we got in Tonga. And below, down below, is actually a histogram of the exposure of different people to this pollution, essentially to the air pollution. It's interesting that 2022, which is when we recorded the highest exposure, I think it coincides with a volcano eruption in Tonga. So it makes sense to us, at least conceptually, you know. Just coming to the end of this part, the last bit I mentioned, you know, the role of agent-based models to simulate what is the impact of the environment and why it's important to, you know, to think of this as agents, not just as, you know, sort of static data, so they can react and things happen to these agents and they react to them. So as an example, this is a simulation or sort of an animation that describes a very simple pathogen X. So it's an artificial outbreak that we are spreading in our communities here. You know, given the level of granularity, we can actually explore even how many people are being infected in a specific location, like a cafe. You know, as you can see there. Now, this same capability is actually something that we are currently using. We started last year working with the Public Health Agency on understanding the resilience of the country to a potential measles outbreak. Now this year, this piece of work became a lot more relevant since we do have an ongoing measles outbreak in the community. And so we are leveraging this model to inform the Public Health Agency and the National Public Health Service on essentially the progression of this measles outbreak and, you know, the potential impact of improving, you know, for example, improving the level of immunization and so on. You know. Now let me just quickly diverge into the topic of sovereign AI, because it's still relevant for ALMA, but just a very small parenthesis. Sovereign AI is something that is coming up a lot lately. People are talking more and more about this. Again, you know, everyone will have a slightly different definition of sovereign AI, but I think basically it talks about our ability to design, to run, and to govern AI systems using local infrastructure, local data, local expertise, you know, etc. Now, I was saying that lots of people are talking about this these days. You know, these are all extracts from the media, just from a few months ago, essentially, you know, talking about the need to essentially have a stance against, you know, the role of big tech companies, you know, essentially completely dominating the AI market and the AI services that are available to us. So what can we do? You know, and I don't have an answer for that. You know, it's a great topic for discussion, and certainly not going to debate it now, but at least I can tell you what I think, first of all, what I think the idea behind sovereign AI would, you know, I mean, building this capability internally can impact economic productivity, right? In the sense that onshore capability raises productivity, creates high-value jobs. It's very important for New Zealand, but also because you build a robust skill base, you start building IP, local IP, right? Supplier networks, essentially. You know, there's a national resilience and security argument for sovereign AI. Obviously, data sovereignty is kind of the obvious benefit of this, you know, keeping sensitive data under NZAI jurisdiction, Maori data sovereignty, and holding te tiriti obligations, you know, and also cost efficiency and latency, which is also an argument that you can make. Onshore inference and fine-tuning smaller models can reduce cost and model latency. So what are we doing about this? From our small corner at PHS Science, so we started building this on-site or on-prem capability we're leveraging, we have HPC resources in the organization. They're modest, but we do have GPUs. On top of that, we're also exploring with alternative to GPUs, particularly Mac Studio machines, the M3 Ultra machines that have 512 gigabytes of unified memory between CPUs and GPUs. So that gives you access to incredible amounts of RAM to host and do model inference, perhaps not with the same performance of a GPU, of an NVIDIA GPU, but at least you're able to do it, right? And to be honest, the performance cost is about a factor 2 compared to a GPU. So it's not a huge cost for most of the use cases, And we are running, our own, open web UI and chat service for our organization. And more interesting is about all the services that you can build with this in the backend, with hosting all these open source large language models, right? At the moment, we call this AI Lab, and we have a general chatbot that provides lots of different capabilities for our different business users. Business groups within the organization, but also custom services, right? Like automated report generation, secure document queries, tabular data interrogation, which is something very similar to what this Weka AI capability was showing yesterday. And also the ability to leverage, hosting local models just through APIs, right? So for coding assistance, that can be embedded into your IDE, or also as an API to other platforms like ALMA. So in that sense, we've also embedded a chatbot, an AI assistant into ALMA, which is fully embedded in and interacting with the user interface. So it's not just a chatbot, but it's also something that you can use to navigate within the platform itself, and also ask questions like you would to a normal chatbot, as you can see. So I'm going to go quickly here because I'm coming to the end. But just wanted to highlight this other use case where maybe you're particularly interested in this SA2. You can actually leverage this chatbot capability. Richard was showing this yesterday, and to get a full breakdown, of the demographic attributes of that particular SA2, and then you can export this as a Word document if you want to share it with others. So really cool capability. Now, coming to the end, just wanted to briefly talk about this concept of a national digital twin. So far I've been describing what a digital twin project looks like and why we thought that creating a digital twin of the population was important. The next also iteration of this is to start thinking about an ecosystem of digital twins. And this is something that kind of pushing from within the AI forum as well, from within that architecture, engineering, and construction group, because there's lots of expertise and lots of connections with other digital twin projects, that in the built environment, for example. So we've come with a bit of a roadmap for how we see this being planned over the next few years. At the moment, we are kind of at the bottom, where we're still mapping, who are the key players in New Zealand, or who are the key players that have strong connections with international experience. So, for example, Australia, Singapore, and Canada, the UK, as I mentioned before, and India, they all have incredibly interesting national digital twin projects. And by national digital twin, I mean digital twin, a system of digital twins that can be connected with each other. So think of a digital twin of an underground system connected to a digital twin of the transport system, or connected with ALMA, to understand the impact, of water pipes on social dynamics, for example. So there are lots of synergies that we can leverage when we are able to connect these things. Challenges are multiple. Data standards are one challenge, and actually AI could become a key to unlock the challenge of data standards. So we might be able to relax that need for everyone to have to adhere to a fixed set of standards. building trust and building a trust community where people can actually share would be really important. But for all of that to happen, we need to have proof of concepts that we can champion, to demonstrate value. Ultimately, I think that this National Digital Twin Initiative is not something that should be hosted by the AI Forum. I think it should be should be hosted by a government agency, a government authority, and it should have proper support. So, but we'll see how that goes. So at the moment, there are a number of organizations that are interested, and we are, in the process of defining where we go next with this. So that's basically all that I wanted to mention in terms of sort of a summary. 4 little points. Digital twins went through the trough of disillusionment, as I showed before. ALMA illustrates that AI can be a force multiplier for digital twins. Investment in sovereign AI can secure a future of AI innovation for Aotearoa. And 4, the National Digital Twin Initiative seeks to build an ecosystem of interconnected systems. And I would be super happy to have more of a discussion on that if you think that your expertise, your connections, or if you're just interested in learning more. Just want to finish just by showing you pictures of humans. Because there's lots of actually real humans, not virtual humans. We've over the past couple of years, we've gone through a lot. We started with ALMA from scratch, and it wasn't easy, and we've had to fight lots of different battles. But it was, for example, particularly rewarding, having being recognized, for example, with the Aotearoa AI Awards earlier this year, because that kind of really pushes you or gives you the motivation to continue pushing the bounds. So thank you very much. That's all.